Let me check if I'm properly audible. Hello.
Hello.
Yeah. Okay. Okay. I think it's fine. So screen. Okay. So welcome to the 12th class on electromagnetic theory. And yesterday, or like the last class, we had a revision class, which was an extra session where we tried to look at, uh, a- in a very concise way, all the basic concepts and important concepts that we had discussed throughout the course. Okay, starting from electrostatics to uh, electromagnetic waves, their transmission, propagation, transmission lines, waveguides, and so on. So we did discuss and revise the basic concepts yesterday. So today's class will be on sources of radiations, which is like if you talk about antenna, if you talk about some accelerating, or like some radiating dipole, right? So that acts as a source of radiation, and we'll try to see how, based on the direction, based on, obviously direction is also there, but also the distance from the source, how the field changes. Okay, so there are different regimes that can come up based on the distance from the uh, radiating source. Okay, and we'll see that because it takes, like, the speed of light is a finite quantity, so it takes a finite time for any signal to propagate from one point to another, and that's why the very concept of retarded potential comes in. Okay, when you have time varying situations, so we'll also discuss about that. Before that, we'll start with understanding you know why scalar and vector potentials are useful, and how, while keeping the fields like the same, while not changing the exact physical condition, one can choose certain ways of defining the scalar and the vector potentials, which can simplify our uh, you know calculation of the fields quite to an extent. Okay, so we'll talk about gauge transformations, which allows us to do that. So that is something which we'll try to do today. We'll also solve some basic questions. Majorly, this part of the course, whatever we discuss, there are either very straightforward questions based on certain formula, or it's quite straightforward. So we'll try to discuss the concepts and solve certain questions. To introduce myself, I am Sauravi from Indian Institute of Science, and this is a TAship course that I'm trying to take uh, as a part of my PMRF TA requirements. Okay, so yeah, so let's get started with today's class. Yeah, so first of all, we know this is how. Okay, let me choose the. Okay, so first of all, we know this is how the Maxwell's equations look like, right? So you can write it in terms of electric and magnetic fields, and these are the four equations. We saw how we get to this point. We also looked at it yesterday as a revision as how these equations were derived. We did derive all of them in our course, right? But now the point is that if we want to write this Maxwell's equations in terms of the scalar and the vector potentials, okay, how will they look like? That's the first thing, right? And why we want to do that is because we ultimately want to write electric and magnetic fields in terms of the scalar and vector potentials, and because they're easier to you know deal with. If you just we know that suppose if you want to find the electric field at a certain point, it's much easier to first find the potential, which is a scalar quantity, and then find the electric field from there, right? Similarly, vector potentials, you can add certain conditions to it. If you remember last class also, we did discuss this fact that you can choose your vector potential to be divergence-less, right? So you have the freedom of choosing or adding new properties to this vector and scalar potentials, as long as your fields, like as long as the electric and the magnetic fields associated with it do not change, right? And you can make these changes or modifications to the scalar and the vector potentials to suit your will, to make things simpler. So that makes it easier for us to work with scalar and vector potentials. Okay, so what we are trying to do currently is we are trying to find a relation which relates the vector and the scalar potentials with the electric and the magnetic fields, and then also write the Maxwell's equations in terms of the vector and the scalar potentials. So now what the first thing is, we know from the definition of vector potential that B is equal to curl of A, right? Now, if this is because B is divergence less and we can always write it. So this is there. Now, what you can again do is you can put in this criteria, like put in the expression of B in terms of A in the third Maxwell's equation. Okay. And what do you get? So curl of E is equal to minus del T of curl of A. Just you have replaced B by curl of A. Okay. So now you can take, you know, this to the left hand side, and like with the rearrangement, what you get is a new quantity which is like E plus del A del T, and now curl of this quantity is 0. Like this is what is coming from the Maxwell's equations. So now we know from our knowledge of vector algebra that if there is something whose curl is 0, you can always choose that quantity to be gradient of some scale. Okay, so here what you can do is, because we know we have also done similar things in during electrostatics, right? When curl of E was 0, you could write E as minus grad V. So now for this case where you do consider this temporal change, what you see is a new quantity, curl of E plus del A del T, which goes to 0, right? So E plus del A del T is equal to minus gradient of a scalar quantity. And this is, you can choose this quantity to be a potential. Okay, so that means now the initial equation for the electrostatics was just E equal to minus grad V, but now it gets modified, right? And because you have this temporal changes coming in, so it gets modified by this equation, to this equation. Okay, so that means now if you know V and A, you can write the magnetic field, or you can find the magnetic field, and you can also find the electric field, right? So this is how the scalar and the vector potentials are related to the expressions related to the electric and the magnetic fields. Okay, now what you can do again is you can put in this expressions of electric and magnetic fields in the Maxwell's equations, right? So suppose if you put this equation, this expression of electric field in the, okay, so what we are currently trying to do is we're trying to use the scalar and the vector potentials and write the electric and the magnetic field in terms of the scalar and the vector potentials. And we also want to represent the Maxwell's equations in terms of these scalar and vector potentials. Okay. Why do you want to do it? Is because dealing with scalar and vector potentials is much easier than dealing with electric and magnetic fields directly. Okay. So this is something we already know. B is equal to curl of A. And if you put this expression in the in this Maxwell's equation, you'd find that you get a new quantity which becomes which whose curl is 0. So you can again define E plus del A del T as minus grad V. So then initially in the electrostatics you had something like this, but now it gets modified with this extra term which takes into account the temporal changes, right? So this is how electric and magnetic fields are related to A and V. Okay. Now, if you put in these values, these expressions in the Maxwell's equations, you would get the Maxwell's equations in terms of the scalar and vector potentials, right? So how will that look like? So if you put this equation 10.3 into the first Maxwell's equation, okay, then you would get something like this. So this is one of the relations. Again, if you put the expression of electric field and magnetic, yes, okay. So if you again now put in the expression of electric and magnetic field in the fourth Maxwell's equation, you would get something like this. And you can understand it's quite complicated, right? It looks quite complicated. If you rearrange it, you would get two terms. Out of this, the first term is comparatively simple because it has a form of wave equation, as you can understand, right? It's similar to the wave equation, but then you have this additional term here, which tells you that it's a complicated differential equation. It's not very easy to solve for A from this equation, right? But one interesting thing, or you can say important and useful thing about this potentials is that the absolute value of the scalar or the vector potentials is not important, right? Whether your potential is, like, you can always add constants to your potential. Suppose your potential was some you know some non-zero quantity, you can choose options. Okay, so now let us move forward. So as of now, we know how magnetic field and electric field can be written in terms of the potentials, and this is how the Maxwell's equations would look like. Okay. Now, because these equations are complicated, right? Solving these equations are not very easy. So that's why what we will do is we'll try to choose or take certain, add or impose new conditions to the potentials so that these equations become simple. Okay. But keeping in mind that the electric field and the magnetic field should not change. Okay. So if we can ensure that the electric field and the magnetic field do not change, you can always add new terms to your vector and scalar potential. Okay. So that is what we'll try to do. And in that process, we'll try to simplify these equations. Right. Okay. So that can lead to different kinds of gauges. Okay. So suppose if initially you had some, you know, so there can be different set of potentials like VA and V prime A prime. Both of them can correspond to same electric field and same magnetic field if the difference between this and this potential follows certain conditions, right? So if you say that A prime is A plus alpha, V prime is V plus beta, then you know that curl of alpha should go to 0 because we know that B is curl of A. So B should not change. So that tells you that your alpha should have a 0 curl, right? So that in that way you can write alpha as a gradient of some scalar quantity. Now you also have to look at electric field, right? Now electric field has this dependence. So this tells us that if your electric field has to be the same, then you know this term here, okay, it should be divergence less. Sorry, the gradient, what am I saying? One second. This is some scalar quantity. Alpha lambda is some scalar quantity. So d lambda dt is a scalar quantity, okay? And beta again is some scalar that you have considered some added scalar to your potential. So this term is I don't know if my charge, oh, one second. My net charge of my laptop is going to die. 1 second, sorry. Yeah. Any question?
Yeah, madam, will you cover retarded potentials also? Follow
Yes,
in the following
yes, yes,
lecture.
yes, as we proceed.
Okay, okay.
Yeah. So then now what you can do is basically your beta, which is another scalar that you have added to your vector potentials, should follow, should have a, you know, zero gradient, right? So, so that tells you that it should have a form like this. Now you can add some new constant k to it. You can also absorb this constant in your lambda, but basically now that means that you can have new vector and scalar potentials, or different set of vector and scalar potentials which differ by forms like this. Okay, some scalar, so you can have a gradient of some scalar here, and then you can have time varying term of that scalar with added to your potential. Okay, so if you have such kind of things, both these vector potentials av and a prime v prime, both of this pair of potentials will correspond to same electric and magnetic field. Okay, so this kind of transformations, the freedom to add these terms, this is one of the examples, or or you can say the fundamental idea of gauge transformations. Okay, so now what happens is, so if this is possible, now what we can do is we can make some modifications so that these equations become simpler, right? So for the first case, what we can do is you can take your a to be divergenceless, right? So if your a becomes divergenceless, then this becomes a much simpler equations, which is like your Poisson's equation, right? So that leads to your, so these are very, there are many popular gauges, and this is one of the popular gauge, which is called the Coulomb's gauge, where you choose your a to be divergenceless. That gives a very, this is your well-known Poisson's equation. Okay, so now you know how, we already know how to solve it. We had solved for Laplace equations as well, so similarly we can also solve for Poisson's equation, and this is comparatively way simpler than solving this, right? So you can solve for this, and it would have a similar kind of form. So if you consider some charge distribution of, with the volume charge density rho, and then this is how your potential will look like. So you can solve that. But the problem with this gauge is that while solving for V is quite simpler, solving for A is not that simple. Okay. Why? Because if you put in this condition in this expression, this term would go away, but still you would have many terms in this equation. And so solving for vector potentials in using the Coulomb gauge is not that simple. Okay. So another such gauge is the Lorentz gauge, where what you do is, so you can see, if you look at this equation, it would have been much simpler if this term was not there, right? Then you would have some inhomogeneous term on the right hand side, but this would be just your wave equation, much simpler to solve. So that's what we do. So we take a condition where we say that divergence of A is equal to minus of this term. Okay, so that this term goes away, right? So that's your Lorentz case. So if you do that, interestingly, you get a form for the like equation of your vector potential and scalar potential looks like this, which is interesting because this tells us that this particular gauge treats V and A on equal footing. So basically now what you can do, you can solve for V from here, and you can solve for individual components of A. Okay, so three components, A, X, A, Y, A, Z. So in a way, if you solve for this four equations from here, you would get the information of E and B in a by doing much simpler calculations. Okay, so now this, because they take similar form, you can define a new differential operator like this. Okay, which is given as del square minus mu naught epsilon naught del square del t square. This is called the D'Lambertian operator. So now this is your form. So if you use this Lorentz gauge, then this is the form that your potential have. And if you can solve for the potentials, you can again go back and solve for the electric fields. Okay, so that's the basic idea of why it's important and useful to involve or include these gauges in the potential calculations. Okay, so this is something what you just referred
One
to.
sec. What is the
Yes,
symbol of that square? Square is there apart from del. That's it. What is the name of that symbol?
this is called the D'Lambertian operator.
Okay, okay. Operator. Is it a vector operator or scalar operator?
So it is like, what do I say? So it has both kinds of things, right? So I mean, see, it's operating on the vector potentials as well, and it's
Okay,
also operating on the scalar. So because you have this del square term also,
okay.
so it's like the del square operator plus
Mm.
time derivative. So time derivative you can do for any quantity, and
Okay.
del
Mm.
square also you can solve for both scalar and vector, right? So yeah.
Okay, okay. Yeah, thank
So it's you're just defining a new operator for this term just to simplify your equation.
you. Got it,
Okay.
got it.
Yeah. Okay. So now if we look at you know this kind of forms, okay, so if you consider the static case, so consider the case where you don't need to have the temporal change, so this term goes away. So basically you can have a form like this, right? So this is like four copies of Poisson's equation, right? This is something which we had already known during our electrostatic calculations. And now because you have this vector potential also, it has a similar kind of form. Okay. So now that means you can write an expression for vector, like the scalar potential and the vector potential in terms of the charge density and the current densities, right? So this is the typical relations, right? Now the question, the problem, or the important point comes in when it is not static anymore. So consider the case where you know this rho or this j is changing with time. Okay, then what happens? So if your rho is there's some rho here and it is changing with time, you are trying to find the field somewhere out here. Okay, now the change in rho will not be immediately reflected in the field that you see here. Why? Because we know that electromagnetic waves travel with a finite speed of c in vacuum, right? That's the maximum speed that it can have. So it is traveling with the speed of light. So now based on this distance from the you know your charge distribution or your current distribution, it will take some finite time for this change to finally get reflected at your field point where you are trying to find your field, right? So that means you have to consider what happens at a initial time. It's some change that happens at the initial time, which is getting reflected at this point when you are measuring at a certain time t, right? And what is this delay? It depends on what is the distance, okay, how far you are by c, right? Basically how long is it taking for the wave to you know travel, right? So this time is called the retarded time. So basically what it means is that now if you have a non-static situation where at your source things are changing with time, so there your expressions, like this expressions, will now get modified. How? So you would say that the potential at some certain point r at time t is basically 1 by 4 pi epsilon 0 integration of rho at the field, like at this position where you had your charge or current distribution r prime at some earlier time tr, okay, and then d tau by r. So basically it's the charge distribution or the current distribution at some earlier time which is determining the potential, right, or the fields in a way. So that's the concept of retarded potentials, right? We are talking about retarded time because it's something which has happened earlier. It's taking some time for that information to reach us. Okay, is it clear?
Yes, madam.
Yeah. So now that means, suppose if you have, this is some one of the examples of, you can say, source where you have a Hertzian dipole antenna. Now basically what it means is, suppose you have some current source here. Okay, it has a particular dimension delta z. Okay, so basically in the last case, if I compare with this form, okay, so this jd tau, right, can be replaced with something like I dz. So there is some current element with a certain dimension delta z, right? So that's your source. Now the question is, what is the, what is its effect, or what is the potential, or what is the field at some later point, which is at a distance r from this source, where, now it depends. So if your r is significantly larger than this dimension, then you are in a limit where you can, where this dimension won't play much of a role. If you are comparable to the dimensions, then the dimensions will play a role. So first we'll take the condition where, delta z is much much smaller than r. Okay, so the dimension is way smaller than the distance from the field point to the source. Okay, so now what you can do is, we want to find the fields, right? So we'll first find the potentials. So we know the expression of the vector potential. This is how it looks like, right? Now, because, things can change, so you will have a retarded potential coming in. So we do have to consider the fact that things can change with time. Okay, temporal changes will be important. So now what you can do is basically just use this expression, right? And here when you write j, you can replace j d tau or dv by I dz z cap. Okay, so you can understand that this tells us that your A should be along z. If your current element is along z, then A should be along z. Okay, so you can first start with a, cylindrical coordinate system, and then, or you can also move to, spherical coordinates. That is something which we'll do as we proceed. So here you can see that because of the symmetry of the problem, you have a current carrying element at z, so A is along z, because it's the direction of j, or the current element, which will govern the direction of your vector potential. Okay, and if you want to write it in, like, in the change from, cylindrical to spherical coordinates, or like have a coordinate transformation, or Cartesian to spherical, you can use this idea of, if this is az, so you can take cos theta and sin theta components to find the radial and the theta components, right? So before that, if we just now want to find az, okay, so what we do is, we can replace j dv as I del z. Okay, and because you have a wave, right, at this source, you have a wave, so it has a form of something like e to the power j omega t minus kr, or beta r. So beta is, here is your is a wave vector, so you can write beta as 2 pi by lambda. Okay, so it depends on the signal, or the wave that you have at the source. Okay, so it has a form like this. So this is how your uh, signal at the sources, and that's how it's propagating. So you take up this form. So now what you can do is, you can rewrite it as something like this, right? Where I, so this term here, so see, other things come out of the integral, because, delta z is a constant quantity, you can just take it out. This does not depend on delta z. So basically this term here, this will be your retarded current. So with time, it will look something like this, right? Why retarded? Because see here, this, you can always, this beta r, right? It talks about a phase of your signal, right? And that phase carries the information about how far you are traveling from your, you know, source. Okay. So basically, you can always replace beta. Beta is like k. So you know omega equal to ck, right? Normally for a wave, omega is equal to ck. So you can write k as omega by c, right? And then you can take omega common. So you can see that now basically what it is telling you is this is some current at some earlier time given as like the time difference is given as r by c, where r is the distance between the two. Okay. So it's the current at some earlier time which is governing the potential at the given time t. Okay. So now once you know az, you can do coordinate transformations and write it as, sine and cosine terms, and then phi component will go to 0. So you can do this kind of transformations because, you know, in many cases spherical coordinates are widely useful. You can see how, if you consider a sphere around uh, this source, how is the waves getting distributed, what is the power distribution and all of that. So in that way it's interesting to go from az to a theta a phi ar. Okay, a phi will be 0, so you have ar and a theta. Okay, so now once you know the vector potential, you can use it to find your uh, magnetic field, right? So here we are trying to find the auxiliary field because we are concerned about, what happens from the source that you are having. So you can just find H. Okay. And this is just typical, curl operator in the spherical coordinates that we are trying to solve. Okay. Now, when you solve for this, what you will get is an expression like this, right? So this is your expression of H phi. Now, it is interesting because now you have a 1 by r term, you have a 1 by r squared term. Okay. And that means based on what is the distance between the source and the field point, different terms will be playing a dominant role based on this distance, right? Now you can also find the electric field. Okay. So this comes from the Maxwell's equations. So once you know the magnetic field, you can also find the electric field because you know the frequency of your wave and the medium properties. So you can do this to find the electric field components. Okay. So this is your radial component, this is your theta component. So again, here you have 1 by r squared term, 1 by r cubed term, and also like all these combinations. Now, based on the value of r, different terms will be dominant in different regions. Okay. So that gives rise to this different regions. So you can have far field, near field, or intermediate region. So that means now at the far point, you can understand that only, if you look here, the 1 by r term will be the dominant term. Okay. Hmm. So at the far field regime, the radial components only have 1 by r square and 1 by r cube term. So this will almost go to 0. So it will not play an important role. Here only this term will be the dominant term. Similarly, here you will have this term as your dominant term. Okay. So this is how your expressions of the different components of electric field and magnetic field would look like. Okay. So now we know that if you want to find an expression for uh, the Poynting vector, we know that it's given as half of real part of E cross H star, right? So if you do that, you can see that what would happen? You have a 1 by r here, you have a 1 by r here. So you would have a 1 by r square coming in here, okay? And because there'll be a cross product between like phi and theta, so it will be in the radial direction. So that means your the energy propagation is happening in the radial direction. Okay, and you would have this sine square term coming in, right? Sine theta into sine theta. So you have a sine square theta term coming in. Okay. So now if you do the power density, okay, so you and try to find the total constant, like total average power, if you want to do that, what would happen? You would have a 1 by r square, and then if you multiply by again 4 pi r square dr, that's your volume element for a sphere. So if you do that, you would see that it's a constant average power. Okay, so that means that the far field regime, it will look like that it's a constant average power that is getting radiated from the antenna, and it would not depend on the distance anymore. Okay, the power density will not be dependent on the distance, and this will be the typical expressions for your uh, electric fields and magnetic fields, right? Now you can also be in the near field regime. So there, what would happen is the r cube term will be dominant. Okay, so if we look here, so this will be a in point, and then here you have a 1 by r cube term. So er is proportional to 1 by r cube, e theta is proportional to 1 by r cube, and while the magnetic field would almost be negligible. So that means in the near field regime, it's almost like an electrostatic field where the electric field is playing a major role. Okay, and what you can do is you can consider a dipole element. Okay, so consider this contribution is coming from some dipole p. So that means er and e theta can be written in terms of some p cos theta, p sin theta kind of terms. Okay, so it's like the the your uh, source, or this antenna would then have a would look like a dipole, and so like the dipole equivalent. Okay, and there's also an electrostatic field in the near field. Okay, now there can also be an intermediate regime. Okay, where what happens is 1 by r squared dominates. Okay, so this is the case where, if you look at, so you would have this all this, beta r terms here, right? So under this condition, beta r is tends to 1. So that means this tells us that if your distance between the field point and your source is comparable to 1 by beta. Okay, and beta is related to the wavelength of your signal. Okay, beta is equal to uh, 2 pi by lambda. So from there, you can say that if your distance r is comparable to lambda by 6, then this is the regime which is called the intermediate regime, and there 1 by r squared dominates. Okay, so these regions, what happens is here, if you look at, so all these terms become constant quantities. Okay, so they don't really radiate power, and these are like inductive fields, how we call it, because it's like storing energy in that regime. Okay, and so if you are asked whether you are in the far field or in the near field, so you can look at uh, this value. Okay, so in your question, if the wavelength or the frequency of your signal is given, and you have said that you are this far from your source, whether you are in the near field or far field or intermediate regime, so then see if if this distance is comparable to the wavelength, or it is way larger or smaller, right? So that's how you can choose the fields. So suppose based on this different regime, you have to choose the expression of your electric and magnetic fields. Okay, so there can be various questions like that. So in those cases, that's how you decide which expression to choose. Okay, now the dimensions of the antenna is quite important. So if the dimensions are comparable, then you can understand that each sections of, like, the antenna, like, you cannot anyways just consider it as a dipole, point dipole kind of thing. So then the dimensions by itself will be important. The distribution of uh you know of the fields around it will be important. So in a way, if d is the dimension of the antenna, then if r is much greater than 2d square by lambda, that's your uh, you know diffraction regime, or you know the regime where you can consider it to be uh, you know dipole antenna kind of thing. Okay, and in those cases you can always find an expression for the power. Okay, now if in nature it's like when we define, so if you have an antenna, if you are asked what is the power that you have, so or the intensity of your radiation, so you always have to do average. Okay, so it's not just the s value which is important, but the time averaged value, and it's given as half of real part of E cross H star. So now once you know the expressions, so suppose here, so we already know the expressions, right? So from here you can define an expression for the Poynting vector. Okay, now you do know that the ratio of electric to magnetic field is called the wave impedance, right? And in free space the wave impedance is given as 377 ohm. In a different media, okay, this will change. So based on, so there comes the effect of the media. So if you have a different media, then you have to multiply. So what is this n naught? This is basically a ratio of root over mu by epsilon, right? So for free space it is mu naught, root over of mu naught by epsilon naught. In a different media it would change to root over of mu by epsilon, some other value based on the permeability and permittivity of the media. So accordingly this term will change. So similarly you would have terms changing here, right? So now if you know the expression for electric and magnetic field, you can just write the expression for the Poynting vector, and this is how it would look like. So what you can see is that the average value has this sine squared dependence. Okay. And now if you want to find the power coming out of some volume element, which is given as r square sine theta d theta d phi. So it's like if you consider a solid angle and then say what is the power coming out from that region. So then you would also have to multiply by this element. So you would have a term like this. Okay. So in order to find the total power, what you have to do is you have to take a integration of theta from 0 to pi and phi from 0 to 2 pi. And if you do that integration, that's the total power that is radiated by your source. Okay, so that gives you a value like this. So you can see there is no radial dependence, right? And this is something which we had also seen here, because you would have a 1 by r square, and once you multiply by r square, this r square gets cancelled out. So the total power radiated do not have a radial dependence, and it's a quantity like this. So what does it depend on? It depends on the current that is flowing in your antenna, the dimension delta z of your antenna, and the radiation resistance. So your wave impedance eta naught. Factors govern term by I squared. What is left is like a resistance. Okay, so in a way you are considering your antenna as some resistor, and what is that radiation resistance? That's given by pt divided by I square. Okay, so now in different questions there can be very straightforward direct questions where you know I is provided, delta z is provided, or the frequency, and the frequency of your signal is given, so you can find the wavelength from there based on the medium. Okay, and then you are asked what is the power radiated, or you are asked what's the radiation resistance. So you can use this relations to find those values. Okay, very straightforward direct questions. Now this is there's a very good book by Cross and Balanis, and this is also referred in the in the course as well, I think. So which tells us that now based on the dimension of your antenna and how different it is from your wavelength of your signal, right? So if they're comparable or if they're not, how small, how big, based on that there are different ways of calculating the resistance, radiation resistance, and these are some of the relations that are very standard and very standardly used. So if your length of your antenna is within these ranges of your wavelength of your signal, then you can directly use these relations to find the radiation resistances. Okay. Now, and important point about, and why I wanted to bring this up is this is not something I think which is in the course or which would be useful for your um, solving the numericals as of now, but it's an important, interesting point which I thought will be good to specify, which is that, sorry, I will just have which is that this power that is radiated by the oscillating dipole or this radiating dipole, it is on the local density of states. What I mean by that is you have this electromagnetic waves coming out from the source, right? Now, this electromagnetic waves, there are certain waves which would be able to, will be sustained by the environment around it, right? And that depends on the density of states, right? So if you just consider a box of some length L, okay, and we know that, if there are certain boundary conditions, so we know that the wave vector components should go as n pi by L, right? So that they satisfy the boundary conditions. So we know that if you now have the same dimension in x, y, and z, we know that the first state would have a wave vector given as pi by L, pi by L, pi by L, right? So in a way, the first, so if you are trying to go to, in the phase space and trying to define a volume, then you can say that the first state will take a volume of pi by L whole cube. Okay. Now, if you want to find the state density, basically you can write it as, so this is the volume for one state. So how many states are there in unit volume, which is just one by this term, right? So V by IQ. Okay. So now in a volume which is given as 4 pi k squared dk. So this is basically in the phase space. Okay. The space which is defined by your wave vector. Okay. So there the number of states would be given as V by pi cube, which is the state density into this volume. Right. Now, if this is the state per unit volume, you can try to find what are the number of states between a certain frequency omega to omega plus d omega. Okay, just changing from k space to like the frequency space, right? And now because you're talking about photons, there can be two kinds of polarizations. So you can multiply this term by two. Okay, and if you're only like we are only considering positive values of n here, right? Negative values don't mean so that's why you're if you look at the entire phase space, you are considering the entire volume, but basically you're only concentrated or you're only limited to the first, what do I say? 1/8 half, where nx, ny, nz, all of them are are positive. So, so that's why you can divide that by 8. Okay. So basically, this is your density of states. So this tells us that these are the number of states that is possible from omega to omega plus d omega kind of thing, right? So, in a way, if we look at the expression of your, you know, this is your expression of your power that is radiated, right? Now you can also rewrite it in terms of like like considering a dipole moment and then rewriting this in terms of a dipole moment. Okay, so there, if you do that, so you will have a dipole moment. So this P is the magnitude of your dipole moment. You have the frequency here. Okay, this is your medium property. And then multiplied to that, you have this term rho, where rho is basically this density of state. Okay, so it's the same expression. Okay, this same expression, you can actually write it in terms of like this. So which tells us that it depends on the density of states. Okay, so what are the available states for your signal or for your wave? You have a source and there are waves emanating from the source. They are radiating fine. But what are the possible states in the region that is around, right? And that governs what is the power that is radiated. Now, this kind of applications, so there is a why I'm mentioning this is because there's this effect. The fact that if you have an oscillating dipole, the power radiated is affected by the density of states can also be analogous to what happens when you have a, you know, uh, a fluorescent molecule or some, quantum source, right? So even there, when it would this density of state or the fact that, so if you have a molecule and a fluorescent molecule, okay, and that will also act as a source, right? And then based on the density of states that are possible, the fluorescence or the signal, the what do I say? The fluorescence basically can be affected. So that has huge implications in the case that now if you can modify this density of states, okay, so if you can change the density of states, you can actually change the fluorescence and then the emission from your fluorescent molecules or such quantum sources. So there is an analogous behavior of, so this is in the classical limit that we are talking about, right? But the same effect is also there when we talk about such, fluorescent molecules or small atomic sources. Okay. Now coming back to what we had discussed, so there are all these different kinds of questions that can come up. Okay, and but these are very standard, straightforward questions. So one such question could be that the magnetic field strength is given at a particular point, like a particular theta and a particular distance from your antenna, and it's in air, so the medium property is specified. And then it is asked that what is the power transmitted by the Hertzian dipole antenna of some length, which is given as lambda by 25. So the first point is, from here you can say that the dipole length or the dimension of the dipole or antenna is quite small, much smaller than the distance at which we are looking, right? So we are already in the far field regime. So we will use the expression of fields in the far field. Okay. Now what is provided is, like, the magnetic field value is provided. Okay, be careful about the units. So, and theta and r is also provided, so you know where what field is there, right? Now in the far field, this is your expression of your magnetic field, right? So here, so we know h phi, it's in air, okay, and delta z in terms of the wavelength, okay, r, theta, right? So in a way, you can simplify it to get a form like this. You want to find the power, and in order to find the power, you need to find the current that is flowing through your antenna, right? So you want to first find I. Okay, so from here you can find an expression for I. So all these values are known to you, right? So because delta z is known in terms of lambda, so lambda will get cancelled, so you can solve for it to get your current, right? So this is your expression for the current that is flowing through the antenna. Okay, now the question is, you have to find the power transmitted. So now the length with respect to the wavelength. So what you can do is, if you know current, you want to find power, that means you want to find the radiation resistance, right? So then you can use this relation here and see where you are. So based on the information about how L is different from lambda, we can use this relation, right? So once you use that relation, so now you can put in those values. Okay, so these are like straightforward questions that make use of the formula that we just discussed. Okay. Now there can also be questions like this. So where you have a Hertzian dipole operating at a certain frequency in free space. So the medium property is given, the frequency is given, right? So that means you can find the wavelength from here, right? Be careful about the medium. So if it was not free space and some other medium, then you have to consider the velocity of your wave in that medium and then accordingly find your wavelength. Okay. So for this case, you can always use, nu equal to c by lambda. So c is your speed of the wave in free space, which is 3 × 10⁸, and C by lambda is nu, or you can write C by nu is equal to lambda. So nu is also provided, which is the frequency. So that means you can find the wavelength. Okay. Now it is said that the dipole is 2 meter long, millimeter long. So you know the delta Z basically, and it carries a current I, which is equal to 1 ampere. What are the approximate near and far field domains, right? So basically, you have to find how different your dipole length is from the wavelength. So first is find the wavelength, okay, and see what is the ratio between your wavelength and your um, dipole length, okay, and from there by using this relation basically, okay, you can see whether you are in the what is the value which differentiates the near and the far field, okay. Now there can also be questions like, if you have a short
Ma'am,
dipole.
one question. Ma'am, that first question is your wave. My wavelength I have calculated. It is 0.3 mm,
0.3
and
mm.
yes, C by F, lambda equal to C by F,
Okay.
and your dipole length is 2 mm.
Okay.
So I thought that far field region is greater than 2d square by lambda. Is it right, ma'am?
So
Two,
this value, right?
far field region 2d
Yeah,
square by
yeah, yeah.
lambda.
So
So D
so
is 2
like
mm there.
so D is 2 mm that is provided. Lambda you have found out.
Yes,
So
but that 5 mm in the question options 5 mm is not matching anywhere.
okay, like I have not solved it explicitly. 5 mm is not matching.
Hmm.
Uh, okay, 1 second. So D from here it's gigahertz. You've taken that into account, right?
Yeah, 3 into 10 power 8 by 10 power 10. 10 into 10 power 9, 10 power 10.
Ah, yes.
So it
Okay.
is 0.3
Point 3
meter, 0.3 mm only.
mm. I am getting confused. 1 second. Let me solve it myself.
Yes.
So 3 into 10 to the power 8 divided by, you have 10 gigahertz, so 10 to the power 10. So 0. You're getting 0.03 meter, right? 3 into 10 to the power 8 divided by 10 to the power
10,
10.
10.
So that means 3, right? Meter. So that is like 30 mm. Am I doing anything wrong? No, right?
And then if we substitute in the 2d square by lambda, it is
So
not
no.
matching.
First, what is the wavelength that you're getting?
1 second.
Three into 10 to the power 8
Uh,
equal to C lambda. So lambda is, oh, 1 second. Am I doing it opposite
0.03
or what?
meters, madam. 0.03 meters.
0.03 meter. Yes. So it should be
Uh,
30 mm, right?
30 mm. Wavelength is 30
Okay.
mm. Dipole length is 2 mm.
Dipole length is 2 mm. Okay. And then now,
2d square by lambda.
okay. So
So
4 by lambda is like 30. So are you getting
8 by
2d square?
30. 8 by 30 mm.
Over 0.2, 0.2 something. So now based on the question, near field, far field is R less. No, 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 no. R-
I guess
so the-
option A is correct, but that 5 mm, why
Look
they have
like
given
option A
5 mm?
only, like from the options, but
Mm.
1 second. 5 mm. This is a bit weird. So 1 second.
Okay.
Just confirming something. Mu equal to C by lambda. So lambda is equal to C by mu. I think we are doing it correct only. Wavelength is 30 mm. And if I use this relation, uh, let me use this relation. So beta, what is beta? Beta is 2 pi by lambda. So lambda by 6. What is lambda by 6? Use this relation. See,
Okay.
so if your R is comparable to this value, then you are in the intermediate degree. Okay.
Okay.
If
Lambda by
R
6
is,
means it is 5 mm, and 30 mm by 6, 5
that's
mm.
what I'm saying. If you use this relation, then it is 5. So anything below 5 will, much below 5 will be like the near field, and way
Mm.
above will be the far field. So I think that gives you the answer like this. Right?
Okay. Yes, yes. Okay. So in that case, we can compare with that relation. And one doubt, madam. Generally,
Yes.
in textbooks, I said that the far field components, the field in the far field region doesn't
Mm.
depend on the distance from the antenna. Is it correct? The statement.
Yes. Yes.
But electric field and magnetic fields are proportional to 1 by r. Na?
Yes.
Then r is a distance from antenna. Then how can we say it is not depending on that distance?
The power. So when you are trying to find the power, you have to do like E cross H, right? Like the
That is
pointing
power
vector.
density. In the power density, we'll get 1
So
by r
power
square.
density will 1 by R square. Now you want to
Okay.
find the average power. So when you
Okay.
want to find the average power, then you have to
Integration with
multiply
that
by,
area. Yeah.
uh,
Okay.
so then it will get cancelled.
That means power is doesn't depend on the distance from the antenna.
Yes. The
Not
average power.
individual average power will not depend. The pointing vector will not depend. Not pointing vector, the power.
Average of the pointing vector, the time
Okay.
average, or like the position, like basically. So
Mm.
basically, if you look at just one direction, suppose if you have an antenna, you're just looking at how things are varying here, that's a different thing. And the point
Okay.
that if you're looking at the average of the power that you're getting, basically that's what we measure, right? We don't measure instantaneous things. It's always average.
Okay. Okay. And we use K sometimes for phase constant, beta sometimes. Is there any difference specifically
So
or
beta is nothing. So so beta is basically like, as per this analysis is considered, beta is nothing but 2 pi by lambda,
uh,
which is k.
okay,
Like,
anything is
so
okay,
normally,
but uh,
uh, I mean, you can also write like k, like if just the derivation was in terms of beta. So
okay,
see,
no
because
no
this
difference.
relation, because
Mm.
when you have used this relation, you have already used the same equation, same relation that we use for k, right?
Okay.
How are we getting going from beta r to r by omega r by c? So that means you are
Okay.
replacing beta by r omega by c. That means omega
Okay.
is equal to c into beta, which is same as writing omega equal to ck.
Okay. So a bit confused then where what is K, what is beta. Okay.
No, they are
Mm.
same.
Okay. Okay. Madam.
Just the
Proceed.
base
Madam.
term. Yeah.
Okay.
Now there can also be questions like this where you have again the length of your uh, dipole is given, the current is specified, and it is said that this is your frequency, and you're asked what is the power radiated by the dipole in free space. So that means now you know the relation, right? This is your relation for power. So here you know the dimension of your uh, antenna, you know the current that is flowing. If you know the frequency, you know the beta. That's okay. And it's in free space, so that means you know the value of eta naught is 377. So from here you can basically find the power that is being radiated by your antenna. Okay. So it's a very direct question based on the formula, right? Now the next part says that, okay, so in the same question, if if you immerse the dipole in water, okay, so now that means what is happening is the medium property is changing, okay, where mu is mu equal to mu naught. So permeability is not changing, but the dielectric constant is good. Okay. Now it says that what must be the current in the dipole to maintain the same radiated power as in the free space. Okay. So, like, any idea how how to solve this? If you have idea, you
Uh,
can save.
the same power equation, but
Hmm.
I is unknown, right?
I you have to find such that the power remains the same, but
Same means whatever
because
power we got in the previous question, we have to equate with that power.
yes, but see, if you keep everything same and just equate with this power, then you would
No,
like
no,
you would get the same
neta equal
current
to
I
neta,
equal to 2.
neta equal to neta naught by root epsilon r.
Exactly. So basically the wave impedance will be changed, right? Because the
Yes,
medium has changed.
yes,
Ah,
yes.
so that means it would be changed by 1 by uh, a root over of 81,
Epsilon r.
right?
Yes, yes, epsilon r.
So that means what is happening is basically the impedance is getting reduced
Mm.
here. So if your impedance is getting reduced, that means the same amount of power can be actually achieved with a lower current. Like physically,
Okay,
if you think about it, if your wave impedance is getting reduced, that means you can get more radiated power with the same current, right?
okay.
Like physically, you can understand, right? Wave impedance is basically what is the resistance that your wave is facing as it is propagating. In a way, that's what wave impedance is, right? So it depends on the medium properties. So in a way, it's like root over mu by epsilon naught, mu naught by epsilon naught. So now epsilon, your eta naught has become 1/9 of what we had before. Clear?
Yes, yes. Yeah, impedance is reduced, but we have to maintain same power. That means current has to be increased.
No, 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 no. So if your impedance has reduced,
Okay,
that impedance has reduced, right? So here this term has
reduced.
reduced. So like basically consider that you have a, what do I say? You have a 1/9 here, right?
Okay.
But your power is constant. So now when you want to find the current, what will happen? This 9 will go to the numerator, this side,
Numerator.
right?
Yes, yes, yes.
So that means you need less current. From a from
Oh,
a from a physical point of view, think of the fact that what is impedance? Impedance is basically some resistance, right?
yes,
Now
yes.
the wave impedance has reduced in the media.
Okay,
So that means in order to achieve same power, you would be requiring lesser amount of current to start with. Same
okay, okay.
radiated power, understood,
Mm.
right?
Okay.
So how much will it be? Because you have a I squared term here, it has
Mm.
reduced by 1/9. So that
Okay.
means if
Root
initially it was 2,
uh,
now it
2 by
should be
3.
2/3. Yeah,
2 by 3. Yeah.
clear, right?
Clear, clear.
It's just that, so here you have 1/9, and then when you find I, the 9 goes up. Yeah, okay. So I think that's it. I think these were some of the questions from the last year's assignment that I thought we could discuss. Like there could be several such questions, but generally from this section, it's like pretty straightforward. More interesting is understanding the near field, far field, and all of that. But questions generally are quite straightforward in the assignments as we just discussed. Okay. If there's any particular question, you can ask me.
Nothing,
Okay.
madam. You
So
can proceed.
okay. Okay. Thank you. I think this is the last class. We did have a, I think, revision class yesterday, like where we had a, like revision meaning it was an extra session. So I thought I'll just sum up all that we had discussed throughout the course. So you can go through that to have a concise idea about the course. Okay. And yeah, I hope this was of help. So yeah, thank
Okay.
you.
Can I have your email ID means if you don't mind for any
Uh,
further
Okay, so 1 second. Maybe
in chat
I
in
can,
chat box you can.
yeah, yeah, because, you know, I just want to stop sharing. Yeah, 1 second. Because I don't want to have it in the, YouTube channel. Like, because there'll be some, it will be shared in the YouTube link will be shared, right?
Oh, okay,
So,
okay.
so you can write me at, I don't know, 1 second. Uh, 1 second, just I'm trying to share the, I think that is like, you'll also have some access, like in terms of like, but hello.
Yeah, hello. Yes, madam. It got
Huh.
stuck.
I just uh I just shared the email in the chat box.
Yes, madam. Got it. Got it.
Okay. Thank you.
Mm.
Yeah.
Thank you, madam. Thank you so much.
Thank you. Yeah. Thank you.